Hi everyone. In this video, we are going to talk about the complex gas turbine cycle. There are several ways to improve the performance of a simple gas turbine cycle. They are regenerative scheme, intercooling, and reheating. We are going to talk about a regenerative gas turbine cycle in this video. Now let's have a look at how we can apply a regenerative scheme into a simple gas turbine cycle. For a simple gas turbine cycle, if the temperature at the turbine exit here, T4, is greater than the temperature at the compressor exit, T2, you can see that we have a potential to recover heat from the turbine exhaust. This heat recovery could be achieved by using a heat exchanger. Here in this case, we call it a regenerator or a recuperator. You can see that when we have a regenerator here, we can recover the waste heat from the turbine exhaust to increase the temperature of the compressed air. In this case, T5 will be greater than T2. Now, when the compressed air enters the combustion chamber at a higher temperature, it means that it will consume less amount of fuel in the combustion chamber, or Q in will be reduced. Hence, you can save the fuel consumption and thereby increasing the cycle thermal efficiency. The performance of the heat exchanger or the regenerator can be defined in terms of the regenerator effectiveness. It can be defined as the ratio between the actual regenerative heat and the theoretically maximum regenerative heat, or epsilon equals to actual regen divided by maximum regen. The actual amount of regenerative heat is the actual amount of heat transfer between the exhaust gas and the compressed air. So, it can be calculated from either hot side or cold side. If you calculate it from the hot side, it will be H4 minus H6. In another way, if you calculate it from the cold side by taking H5 minus H2, and they are both the same, or H4 minus H6 equal to H5 minus H2. In this equation, we use H5 minus H2 as the actual regenerative heat. Now coming to the next term, the maximum regenerative heat. It occurs when the heat transfer between hot and cold streams has reached the theoretically maximum possible amount, at which there is no temperature difference at either hot or cold end, which is T6 equal to T2 or T5 equal to T4. Now let me draw separate diagrams to show the condition at which we can achieve the maximum heat transfer between hot and cold streams. There are three possible shapes of temperature profiles at the maximum heat transfer conditions. The first one occurs when MCP of the hot stream is less than that of the cold stream. In this case, we can see that the zero temperature difference appears at the cold end. The exhaust gas from the regenerator will be at the same temperature as that at the compressor exit, or T6 equal to T2 here. On the other hand, if MCP of hot streams is greater than that of the cold stream, the zero temperature difference will appear at the hot end. The compressed air from the regenerator will be at the same temperature as that at the turbine exhaust, or T5 equals to T4. And lastly, for cold air standard assumption, in the gas turbine cycle, in which the air is assumed to be the working fluid, MCP of the turbine exhaust is assumed to be the same as that of the compressed air. The slope of both hot and cold temperature profiles will be the same. There will be no temperature difference at any point along the profiles in this case. These conditions do not actually exist. They only appear in the theory because you cannot have zero temperature difference in actual heat transfer. The maximum theoretical heat transfer can be determined by H4 minus H2. Let's move on to the example of regenerative Brayton cycle. We'll continue from the previous example of the actual gas turbine cycle. Here, we add a regenerator with the effectiveness of 80%. What would happen to the thermal efficiency when compared to the actual gas turbine cycle in the previous example? Now, let's draw a TS diagram first to get a better understanding of the overall process and to identify the information we have and what we want to determine. From the previous actual gas turbine cycle, we'll install a regenerator to exchange heat between the turbine exhaust, or 4A, and the compressor exit, or 2A. As a result of this regeneration, the turbine exhaust temperature will be reduced from 4A to 6, while the compressed air temperature will be increased from 2A to 5. You see that the amount of heat required in the combustion chamber will be reduced. Therefore, the thermal efficiency will be increased. This is an extended solution from the previous example. We have calculated some parameters at actual conditions as shown in the solution map here. To determine the thermal efficiency of the regenerative gas turbine cycle, we already have the actual work required in the compressor and the actual work produced from the turbine, or W1A and W34A, from the previous example. We still need to update the required heat input to the combustion chamber, or Q53, since we have a regenerator installed. Q53 can be determined by an energy balance around the combustion chamber, which require Cp, T3, and T5. We need to know T5, which is the compressed air temperature at the regenerator exit. This could be determined by using the regenerator effectiveness value given from the problems. We have now completely formulated our solution procedure. The calculation sequence can then be followed from the step in which we know all inputs. First of all, using the definition of regenerator effectiveness to determine T5. The regenerator effectiveness is the actual heat transfer divided by the maximum heat transfer. Here in this case, it would be H5 minus H2A divided by H4A minus H2A. When we substitute the term enthalpy change with Cp multiplied by delta T, we'll get Cp multiplied by T5 minus T2A divided by Cp multiplied by T4A minus T2A. From the cold air standard assumption, Cp could be cancelled out. Substituting all known values, which are effectiveness value, T4A and T2A, we can determine T5, which is 688.98 Kelvin. Next, we can use T5 in the energy balance around the combustion chamber to determine the new heat input required, or Q53. Here we have Q53 equals to Cp multiplied by T3 minus T5. And then we can get Q53 at 413.08 kilojoule per kilogram. Finally, we can use the updated heat input Q53 in the previously calculated W12A and W34A to determine the thermal efficiency of the regenerative gas turbine cycle. And we get 31.1% efficiency of this cycle, which is higher than 22.9% in the case without regeneration. So you can see that we have the regenerative gas turbine cycle with higher efficiency than the one without regeneration here. That's all for this video. Thank you for watching. Goodbye.